In problem 5.11, we are told that there's a particle, or mass, at two different positions, x1 and x2, and the speed, respectively, v1 and v2. Now, the mass is m for this mass. Now, we can say that the energy at these 2 points, so energy point will be equals to the kinetic energy plus the potential energy. So the kinetic energy will be equals to 1 half m v1 squared plus 1 half k x1 squared. And the energy at point 2 will be equals to kinetic energy at point 2 plus the potential energy at point 2, which is equals to 1 half mv2 squared plus 1 half kx2 squared. Okay. Now we know that these two energies actually have to be the same because it's a closed energy, so the force from the outside, external, is equals to 0. So the mechanical energy doesn't change, and so it has to be the same at all points. So we can put this equals to each other. So this one, and say that this one has to be equals to the second one. Okay, so now let's try to solve that bit. Now we can get rid of all the 1/2 in front of everything, and then we can move the positions energy on one side. So let's move it to the left. So we have k x1 squared minus k x2 squared equals 2. Now let's move the kinetic energy to the other side. So we have mv2 squared minus mv1 squared. Now let's divide both sides by m, and we get k over m that multiplies x1 squared minus x2 squared equals to v2 squared minus v1 squared. So we can see that k over m is equals to v2 squared minus v1 squared over x1 squared minus x2 squared. And we know that our angular frequency is equal to the square root of k over m. Now we are asked to find the period, and the period we know it's 2 pi over the angular frequency, which is going to be equal to 2 pi times this one, x1 squared minus x2 squared, over the velocity 2 squared minus the velocity 1 squared. And that is our period. Now, what about the amplitude? Well, we also know that when amplitude is at its max, the kinetic energy is equals to 0, and the potential energy is at its max, and that is equals to 1 half ka squared. So this is equal to the whole energy. So we can say 1 half ka squared. Now we could take either energy, so either 1, so energy 1 or energy 2, and we can put equals to the energy that we have. So we can put 1 half ka squared. I'm going to take the energy at point 1, so I'm going to have 1 half mv1 squared, like we said before, plus 1 half kx1 squared. Now let's try to solve it. We can see that we can get rid of all the 1/2, and then we have ka squared, so we can remove the k on the left side. We divide everything by k. So I'll divide it like this so you can see what I'm doing. So we have a squared is equals to m over k v1 squared plus x1 squared. Now the m over k, we just saw it. The m over k is right here. Now we have the opposite, so the only thing we're going to do is literally just switch it. So let me copy this I'm bringing it over here, so it's going to be right next to us when we need it. And so we're going to have x1 squared minus x2 squared over v2 squared minus v1 squared, because we said this is actually k over m, so we have to switch it, times v1 squared plus x1 squared. A squared is equals to this. So if you want a, we put a square root on both sides, and we get x1 squared minus x2 squared over v2 squared minus v1 squared times v1 squared plus x1 squared. Now this is our solution. Now in theory you can work it out and put just one single fraction, but we don't really need that. We can just leave it like this. It is correct.